Hello and welcome to today's lesson looking at electric fields. Now today's lesson is very similar to what we covered in our previous lesson of electrostatics because we're going to be trying to understand the process of electrostatics, but this time from the concept of electrical fields. So in today's lesson we're going to try and understand the basic definitions of electrostatics from electrical fields, understand the rules that govern electrostatics and electrical fields, and then try and look at some of the applications of electrostatics and electrical fields in the real world. So this falls into the following part of the AQA GCSE physics specification. 4.25.2 electric fields, which is found in the electricity topic of AQA GCSE physics. Now please remember that this concept is separate science only. So if you're carrying out combined science, this won't be on your examination. Now, the principles of electrostatics, which we've covered previously, only apply to charged objects. Now, charged objects are objects which produce an electrostatic field, and they're also objects which interact with the electrostatic or electrical field of other objects. So all charged objects exert an electrostatic or electrical field into the universe. Now an example of a charged atom is an ion. Now an ion is an atom with a different number of protons compared to electrons. Now protons and electrons will then be unbalanced if they've got different numbers, and that gives an overall charge to the object. Now there are two possible types of ions: positive ions and negative ions. Now a negative ion is caused by electrons being added to the atom. So a negative ion has more electrons in its structure than it has protons, whilst a positive ion is caused by electrons being removed from an atom. So there are more protons than electrons in this particular substructure. Now, the process of turning a neutrally charged atom into an ion is called ionization. Now, ionization can be caused by the collision of the atom with an energetic particle or with radiation. So, particles or radiation which do this, which turn atoms into ions, they could be electrons, photons, gamma rays, X-rays, alpha particles, beta particles, and we term these particles or radiation as ionizing. So for example, X-rays and gamma rays are ionizing radiation. So all charged objects obey the principles of electrostatics. An atom with a different amount of protons and electrons are called ions, and negative ions are produced by adding more electrons to an atom, whilst positive ions are produced by removing electrons from an atom. And the process of making an ion is called ionization, and this tends to occur when ionizing radiation collides with atoms. Now, this leads to the concept of electrical fields and the electrostatic force. Now remember, we talked about this previously. All forces between objects can be classified as one of two forces: either a contact force, which are forces produced when objects are physically touching, such as friction, air resistance, tension, the normal force, or they can be non-contact forces, so forces produced when the objects can be physically separated. So for example, the gravitational force, the magnetic force, and in the case of today's lesson, the electrostatic force. Now, all objects can exert these non-contact forces by transmitting a field in space. So a field is a region of space where a body can feel a force. So for example, the Earth's gravitational field is a region of space where you can experience the Earth's non-contact gravitational force. And we represent a field with field lines. So here's an example of the Earth's gravitational field strength. Now, the strength of a field is given by its field density. How many lines are found in a particular area, how close the lines are to each other. So in a field, the closer you are to an object, you tend to find that the field lines are closer together, so the stronger this non-contact force. So in this case of gravity, this means the closer you are to the Earth, the stronger the effect of gravity. Now, throughout GCSE and A-level physics, there's varieties of fields you look at, so the gravitational field, the magnetic field, but in today's lesson, we're going to look at electric fields. Now, like mentioned before, any charged object, so electrons, protons, ions, they all produce and are affected by an electrical or electrostatic field. So we visualize the effect of electrical fields with field lines which are drawn as straight lines from the objects with arrows on them showing their direction. Now, any charged object inside of the electrical field of the particle will feel this non-contact electrical or electrostatic force. The objects do not have to be touching. Now, in this example, the electron is negatively charged, so it will produce an electrical field. Now, the direction of the field lines is very, very important. Now, that gives a real good indication of the properties of the charged particle. Now, we draw the direction of the field lines as the direction a positively charged particle would move if it was placed there. So, for example, if we put a positively charged particle near an electron, that means that the positive charged particle would go towards the electron because the electron is negatively charged and oppositely charged particles attract each other. So in this case, the field lines point in towards the electron. So the point is, for negatively charged objects, the field lines always point towards the particle. But if you had a positively charged particle, another positively charged particle would be repelled by being near it. So the field lines all point away. So in this case, for positively charged objects, the field lines point away from the object. Now, how close the electrical field lines are together tells you how strong the electrical force is. The denser the field lines, the stronger the force exerted. So close to the electron, in this case, the field lines are closer together, so the non-contact force is stronger. But further out from the electrical field, so the charged particle, the electrical field lines are more spread out, so the force you feel here is weaker. So if we look at this particular situation here, we've got two objects, A and B. Which one will experience the greater electrostatic force? Well, object A will experience the greater electrostatic force because it's in a part of the field where the field lines are closer together, so the electrical field has a higher strength. Now, I know it's very tempting to say that it's because it's closer to the charged object, and you're not wrong in that particular statement, but it's a more correct version of physics to say that the reason why object A experiences a stronger electrostatic force is because it's in a region of space where the field lines are closer together. There's a higher field strength. Now, just to clarify, the objects will only experience a non-contact electrostatic force if they are charged. Only charged objects experience an electrostatic force in an electric field. So consider this following situation. We've got a proton, we've got an electron, and as a result, we've got a neutron. Now, only the electron experiences a non-contact electrostatic force when inside the electrical field. That's because the electron is inside the electrical field of the proton. The neutron does not experience a non-contact electrostatic force in the field as it's not charged. Now, let's consider this situation here. So, as a result, what do we have? We've got an electron and we've got a proton. Now, both objects are charged and will actually experience the same electrostatic force. And it'll be an electrostatic force of attraction because the electron is negatively charged and the proton is positively charged. So they're oppositely charged, so they will attract. Now, the reason why this is if you remember, all charged objects produce an electric field. So this means both the proton and the electron are producing electric fields. Now, this means that both charged objects are inside or interacting with the other's electric field. So the proton is inside the electrical field of the electron, and the electron is inside the electrical field of the proton. So they both are affected by the other's electrical field, so they'll both experience an electrostatic force. So this means we observe the overlapping of the electric fields of charged objects as electrostatic forces, in this case of attraction. Obviously, if it was two charges of the same type, we'd experience it as the electrostatic force of repulsion. Now, just to clarify, the force gets stronger as the distance between the object decreases, because if you think about it, more of the field is overlapping, and also the higher field strength parts of the field will be overlapping more because they're closer together. So that's a very important idea. When two charged objects are closer together, they experience a greater electrostatic force. If they're further away from each other, they will experience a smaller electrostatic force of attraction or repulsion. Now, we can also explain sparks with electrical fields. So let's consider the following situation. We have a charged object next to the Earth. Now, sparks are caused when there's a high enough potential difference between a charged object and the earth. Remember, you need a potential difference to move charge and produce an electrical current. So if we have a large potential difference between the charge and the earth, now just remember, the earth always has a potential of 0 volts. So to actually change the potential difference between the charge and the earth, they have to change the charge of the charged object, because the earth is always at 0. So if the charged object was at 20 volts and we increase it to 60 volts, the potential difference also increases, because the earth always stays at 0. So the higher the charge of the charged object, the greater the potential difference. Now, the greater the charge of the object, the stronger its electrical field. That's a very important idea, because charge produces the electrical field, so the greater the charge, the greater the electrical field. Now, the strong electrical field causes electrons in the air to be removed. Now, what did we say earlier? When we remove electrons from atoms, in this case, in the air particles, that causes ions to be produced. So this is another process, another way of ionization. So what happens is air is normally an insulator, but when the air is ionized, they become positive ions, okay? It can conduct the charge. So the electrical field of this charged object has ionized the air, and this allows a spark to occur, because this allows charge to flow to where the potential is 0, where you have the earth, and this is what a spark is. So that's how sparks can be explained with electrical fields. So let's consider what we've learned in today's lesson. All charged objects have an electrical field around them, which shows how they interact with other charged particles. An electrical field is a region in space where charges experience a force. Now, fields are usually shown as diagrams with arrows. The direction of the arrow shows the way a positive charge will be pushed. The closer the arrows are together, the stronger the field and the greater the force experienced by charges in that field. This means the field is stronger closer to the object. Now, with the radial field around a positive charge, other positive charges are repelled away, so therefore the arrows are pointing away from that central positive charge. However, if a negative charge is placed in the field, it would attract the positive charge and feel a force in the opposite direction to those field lines. Now, field lines point away from positive charges and towards negative charges. The closer the field lines, the stronger the force exerted by the charged object. Now, if the field is strong enough, charges can be forced through insulators such as air, and a spark will occur. This is what happens during a lightning strike, and can also happen if a charged person touches a conductor. They all work by the same effect. So let's see what we've learned. So a charged object creates an electrical field around itself. The electric field is strongest closest to the charged object. The further away from the charged object, the weaker the field. A second charged object placed in the field experiences a force. The field gets stronger as the distance between the object decreases. And you should be able to draw the electrical field pattern for an isolated charged sphere, either positive or negative, explain what the concept of an electrical field is, and explain how the concept of an electrical field helps explain the non-contact force between charged objects, as well as other electrostatic phenomena such as sparking. So if we've been successful and we've learnt in today's lesson, we understand the basic definitions of electrostatics and electrical fields, we understand the rules which govern electrostatics and electrical fields, and we've looked at the applications of electrostatics and electrical fields in the real world. And with that, we've completed the topic of electricity for GCSE separate science. I hope you've enjoyed this lesson looking at electrical fields, and I hope you have a lovely day.